Welcome everyone to our video on the nuclear model of the atom. Our learning goals for this lesson are as follows. I want you to be able to describe the experimental setup for the gold foil experiment. I want you to be able to take the experimental observations and connect them to Rutherford's conclusions about the structure of the atom, and then describe the key features of the nuclear model of the atom. Before we get into Rutherford's work, just a reminder about the short video that's posted as an introduction to radioactivity and radiation. Radioactivity is not a large part of this course. However, it would be helpful to just get a brief overview on radioactivity before we get into the next part of the atomic theories unit. And the reason for that is because almost all of the experiments make use of radiation in their work. So take 5 minutes, watch that video. I'll put a link up here on the screen. But just a few reminders about two features. So the first one is that radioactive substances emit known types of radiation. I put known in that this isn't just some random thing that scientists didn't know about. By the time that Rutherford's doing his work, and all this work really happened in between Thomson and Rutherford's work, is that a lot was learned about radioactive substances. And so when Rutherford was doing his work with the gold foil experiment, he knew that certain types of radioactive material will emit certain types of radioactive particles. And the radioactive particle which is of interest to us today are alpha particles. And remember, those are a form of radiation with a positive charge. They have a 2+ charge because they have 2 protons as part of their structure. But for our purposes, it's sufficient just to remember that they are positively charged radioactive particles. So let's look at the experimental setup of Rutherford's gold foil experiment. Few things to note about the images that I have on the screen, as well as some of the images that might be on your worksheet. They are largely correct, and they're quite useful for different parts of the explanations here. Often with these images, there are a few little things which are slightly incorrect. And I'll try to point those out so it doesn't lead to any misconceptions. But this one's a nice one because it shows all the key features of the setup. So first thing here is that we have a radioactive source. In Rutherford's case, he used radium, and the radium was encased in lead. So lead blocks radiation, and if you just let a radioactive substance sit out, it emits radiation in all directions. So it's encased in lead, and there's a small hole, an opening, so that the radiation can get out, and that hole is pointed, if I follow this line here, towards the gold foil. Radioactive radium emits alpha particles. So there's alpha particles in a stream of radiation heading directly towards the gold foil. Around the foil is a screen that is coated with zinc sulfide. And the reason for that is that when an alpha particle hits the screen, it would glow. It has a phosphorescent glow. So the research assistant would be sitting in a dark room. They would be running the experiment. And every time that a little spot on the screen would glow, they would make a note of the location of that hit. So they'd just be keeping a tally of how many hits and where each of those alpha particles hit. So there's the setup. So the data which they were collecting, where they were collecting the location of where all the alpha particles ended up after they passed through the gold foil. So this isn't necessarily correct with what happened, but you can just imagine the options here. You could have all the particles stopped by the gold foil. You could have them all just pass straight through. They could bend and curve. They could go in circles. They could bounce off the foil. So all sorts of options here. But let's start off by thinking about what would have happened if Thomson's model of the atom was correct. So let's not worry too much about the diagrams on the top right here, because they're not too correct. Let's think of this one here. Here's the gold foil experiment, and this red line is the alpha particle stream. With Thomson's model, they expected that most of the particles would basically pass straight through with some curving and bending as they went through. So maybe the one thing that's incorrect about this diagram, Thomson's model would predict a little more curving, because as the positively charged alpha particles pass through the atom, they would get deflected a bit by the negatively charged electrons as well. So, but essentially mostly straight through. So Rutherford did observe that most of the particles passed straight through the foil. Every once in a while, though, something happened. You see the data 1 in 5,000, 1 in 8,000. Point is, a very small percentage. A very small percentage were deflected. They bounced back as if they were bounced either back or at a large angle, as you see down here, as if they were hitting something solid. So just look at those numbers for a second, okay? And think about how this experiment would have had to be carried out. You have someone literally sitting there in a dark room watching this happen. And in order to collect all this data, they would have had to be seeing thousands and thousands of hits on this screen. So it's a huge amount of data to get this result. If they stopped after, say, 200, 300, they might have just seen everything pass straight through, and they would never have discovered the nucleus. So now that we've got his observations, let's connect those to the conclusions that Rutherford made based upon these two key observations. So the first idea here is the location of the positive charge. Rutherford concluded that the positive charge of the atom is not spread out, but in fact, it is concentrated in an extremely dense core. And we've referred to that as the nucleus. So this is why we call this the nuclear model, because he concentrates not only the positive charges, but most of the mass of the atom in a small, dense core. And then he separates the electrons. So he separates the location of the positive and negative charges. And the negative charges are in a cloud of tiny electrons. From these conclusions, it forced Rutherford to derive a new model for what the atom looks like. And this is referred to as the nuclear model. The key features of the nuclear model: small, dense, positively charged nucleus. Most of the volume that an atom occupies is simply empty space. There's no matter there. There's no particles. And the electrons are found in a cloud. So not a literal cloud, it's just the term that we use. An electron cloud just means that they're moving about randomly, but they're held in place by their attraction to the nucleus. So there we have the nuclear model. One note about the relative sizes in our representations. It's helpful to remember is that whenever you draw a picture on paper of the nuclear model or the Bohr-Rutherford model, the relative sizes of the atom, nucleus, and electron are not even close to being correct. I think this key point here is the most interesting. Number 2, most of the volume is empty space. An accurate representation of the space that is involved in the volume of the atom is thinking about the atom as the size of a football stadium. So imagine the volume of an atom is the volume that's occupied by a large soccer or football stadium. If that was the volume of the atom, then the nucleus would be the size of a small marble. So when Rutherford says most of the volume of atom is empty space, it's most of it. You've got the marble, you've got the electrons, which are 1,000 times smaller than the nucleus at least, and then the rest of the football stadium is simply empty. So obviously we can't represent those size differences on paper, but it's helpful to keep in mind that when we see matter, when we see something solid, in fact, most of what we see there is actually empty space between those very small, dense nuclei. So that concludes our video on the nuclear model. We'll move on from there to look at the discoveries of the proton and the neutron, and then look at some of the limitations that go along with this model of the atom.